This is a problem about uniform circular motion. So before we dive into the problem, there's a couple of things we need to remember, like how to spell circular. Uniform circular motion. A couple of things we need to remember about uniform circular motion. First, for any object that moves in a circle, in a perfect circle like I've shown, a perfect circle. Any object moving in a circle has some velocity and it has some acceleration. Acceleration, we remember, is the change in velocity over time. So velocity has two parts. It has a magnitude, a speed, an amount, a size to the velocity, and a direction. Direction. Imagine that says direction. Okay. So for acceleration to occur, you have to be changing the velocity over time, or through time as time passes, so that you have a value for the numerator and a value for the denominator. And velocity can change because of a change in magnitude. You can go from 5 meters per second to the right, speed up to 10 meters per second to the right. Or velocity can change because of a change in direction. And that is what we have in the case of uniform circular motion. The velocity changes because of the directional change, not because of the magnitude change. So right here, the speed is something like 10 meters per second. Speed is the velocity, but without the direction. Right here, the speed is 10 meters per second. But in order to get the object to change from moving in that direction to this direction, you have to push it. You have to accelerate it. And the way that you have to accelerate it is by pushing it toward the middle. So the acceleration always pushes or points toward the middle for an object moving in uniform circular motion. And because of that, the velocity, the tangential velocity, and the acceleration, v is perpendicular, v tangential, to the acceleration. Okay? And when we say uniform, we mean that tangential velocity never changes. It is a fixed value. Okay. There's one other thing we need to remember. I'm going to take this all away. And this. And all of it. The centripetal center pointing, the inward pointing acceleration is equal to v squared, the velocity squared. Let's see if I can make a v squared. V squared over the radius of the circular path. Okay, that's how we find the acceleration. Now in this case, we have a 75-gram ball being whirled in a horizontal circular path. Why did I put quotes? Circular, just underline circular. And it has a constant tangential speed. That means it's in uniform circular motion. That means that this equation that I just wrote down, this one, does in fact apply. Find the tangential speed. The rope is angled at 38 degrees over from vertical, or when the ball has moved to right here, it's angled at 38 degrees over to the right. So the angle remains constant. Okay. We are going to use that equation, the acceleration equation. We're also going to use the equation sum of the forces. Actually, let me write it this way first. F net, the net force, is equal to the mass times the acceleration. But what we're going to do for net force, instead of writing F net, the way that we find net force is by adding up, by summing all of the individual forces, but we have to add them up as vectors, okay? Which means we can't just add, if one force is 1 Newton big and another is 3 newtons big, you can't just add them like this. You have to think about the fact that one might be pointing right, the other might be pointing up, and then you would have to use Pythagorean theorem. That's what I mean when we say that we add as vectors. It means we don't do this, okay? So we're going to use those two equations, and in addition, The last thing that we are going to use is, let's see, our right triangle geometry. So the adjacent leg of a right triangle is equal to the hypotenuse times the cosine of theta, and the opposite leg is equal to the hypotenuse times the sine of theta. Armed with these four things, we can easily and quickly solve this problem, which is one of the harder circular motion problems that we could encounter. All right then, let's get started. I'm going to even take away, let's see, I'm going to take away this equation and write down the equations we're going to be using over on the side, just so we remember that these are things we already know. V squared over R, V squared, try that again, and total force equals MA. Adjacent leg is hypotenuse cosine theta. Opposite leg, hypotenuse sine theta. Oh my gosh. This is why I need a different stylus. Okay. The first thing I'm going to do is analyze the forces on... Oh, there's one final thing. Haha, one final thing. Let's say you have a spring like this. If you stretch out the spring, right, it wants to restore its original shape. It wants to be this long. How does it do it? The string will actually pull on its two ends, right? And that force, that pulling force, exists not only in springs that have been stretched, but also in ropes that have been stretched. So if you take a rope and you make it taut, which means it's just slightly ever so stretched, then now the ends are getting pulled back in toward the middle because the string wants to restore its unstretched shape. The force that acts on the ends of a rope which has been stretched is called tension. Okay? And that is the last thing that we need to know in order to get started. So here's our picture on the left. And hey, guess what? There's a rope that's been stretched because the ball is whirling around. So the rope is normally like this long, but now we've stretched it out to that long, which means that the ends are being pulled back with a tension force back toward the middle of the rope. Okay? We will only really care about this tension force at the end where we find the ball. The other end is tied to the ceiling, and the ceiling isn't moving, so it's not much help to us. Okay, what other forces besides tension are on the ball? There's gravity pulling down, like that. And those are the only two, right? Tension and gravity. Now here is the interesting thing. When we have circular motion problems, we can kind of work backwards. Here's what I mean. If the ball's moving around in a circle, right? And here is the center of the circle, right here. Then from the ball, the net force has to be pointing to the center, which is rightward. So the net force has to point to the right. Okay, keep that in mind. Net force points right at this moment in time. We are going to draw again our free body diagram, a diagram with the ball. And we're going to draw the ball free from the other environment. So we're not going to show the string, we're just going to show the forces. And I'm also going to draw the net force pointing right. What provides a rightward net force? Well, clearly it's part of the tension. The tension is at an angle, so it has an x component and a y component. This is the tension, this is gravity. Tx and ty, and the only way that we get a rightward force of the, the only way we get a rightward net force, right? We can cross out that because we drew the components, and the only way we get a rightward net force is if the y component balances gravity. If the y component of tension did not balance gravity, then the net force would not be exclusively the right, it would also have a y part, and that's not the case here. The net force definitely points toward the middle of the circle. Okay, I'm going to draw the tension right triangle Here's the tension. Here's the x part, the x component. And here's the part of the tension that extends on the y-axis, or pulls in the y direction. And this angle is theta. That's 38 degrees. Okay. So the y component of tension balances gravity, but we could replace the y component of tension with t cosine 38 degrees. And the reason we do it is because, in this case of this right triangle, the y component forms or is adjacent the angle. Therefore, we use this equation to make the replacement of ty. Now, the mass is 75 grams. We can replace 75 grams with, let's try this again. The mass is 75 grams, and how do we convert those 75 grams into kilograms? Remember, we can just slide the g over, add in our kilo, but to avoid changing the value of mass, you need a kilo on bottom. But and the reason we need kilo on bottom is so that we have, again, still 75 grams, right? The kilos effectively cancel. But instead of adding a kilo on bottom and a kilo on top, I'm going to add a kilo on top and 10 to the 3, which is equivalent to the bottom. And then I see, oh yeah, to get to kilograms, I have to divide by 10 to the 3, divide by 1,000, and that gives me, as my mass, 0.075 kilograms. For g, I have to put 9.8 here. So we divide both sides by cosine 30 to solve, and let's see what we get. We have 9.8 times 0.075 over cosine of 38. Let's see. Over 38, cosine of 38, and that's 0.933 newtons. Now that we know the tension, we can find Tx, the net force. Right? The sum of the forces, the net force, equals Tx, and Tx we can replace Tx with hypotenuse and theta. We use this equation because Tx is opposite 38 degrees. So Tx then is replaceable with T sine 38. And T we just found to be 0.933 sine 38. So what do we calculate for the total force? Let's see. Sine of 38. And we get 0.57. 0.574. Keep another decimal place. All right, then. Once we found net force, next we find the acceleration. The net force, 0.574. The mass is 0.075 times the acceleration. Divide both sides by 0.075. Divide by 0.075. You get 7.66. .66 meters per second squared. Meters per second squared is the unit for acceleration, or you could do 7.66 meters seconds to the negative 2. Okay, now that we know the acceleration, we can use the centripetal force equation, v squared over r, to find v. V, we easily see, is the square root of the acceleration times r. So the acceleration is 7.66, and we multiply that let me try this again. We multiply, that's a star, by r, which is what? It's half of the diameter, so 4. And what do we get for the speed? We get 5.5 meters per second. And that's how you solve this problem.